Hello grade 12s and welcome to our first lesson in our series of rate of reaction. In this lesson we're going to focus on energy and change. A lot of theory that you have to learn in this lesson that you might not clearly understand initially, so do spend enough time to make sure that you have all the terminology going. We're going to look at rates of reactions, but before we do, let's have some fun and look at the reaction with a pretty fast reaction rate. Okay, here we have a pretty spectacular reaction of potassium in water, where we have quite a big block of potassium that's placed in water. You can see this reaction happens quite fast. Okay, so there are some terminologies that you have to know what they mean, and the first thing that we're going to talk about is what do we mean by the mechanism of a chemical reaction. Now this is a chemical reaction that you have studied in grade 9 when you studied the reaction of carbon with oxygen to give you carbon dioxide. Okay, what happens during a chemical reaction? That is the thing that we are going to look at here. Before we continue with the chapter, it's always a good idea to go to the exam guideline document and see what exactly you have to know. Now, in this exam guideline document, as you can see, you are given a lot of definitions, and in this lesson, we are going to focus mostly on these definitions. We're going to define the heat of the reaction as the energy that is absorbed or released during a chemical reaction. Delta H actually means energy at the end minus energy at the beginning. We're going to look at the definition of an exothermic reaction, and that is a reaction that releases heat. As we had with this fire burning, it releases heat all the time, therefore it's an exothermic reaction. In an endothermic reaction, that is a reaction that continuously need energy to happen. So typically you have done in grade 9, also already in a little bit last year, the electrolysis of copper chloride. You have to put an electric current through that reaction all the time, supplying it with energy for this reaction to happen. And that is called an endothermic reactions. And you will have to be able to classify reactions as endothermic or exothermic. And then you'll often see in examples that we've just talked about delta H, which is the reaction heat, or the heat of the reaction for a reaction, but they will state to you they will give you an equation for reaction and tell you delta H is greater than 0. And then from that information, you'll have to conduct, because delta H is bigger than 0, this is going to be an endothermic reaction. What am I talking about? How do I know that delta H bigger as 0 is going to give me an endothermic reaction? Okay, in an endothermic reaction, energy is being absorbed. So that means your energy for your products right at the end is going to be more than your energy of your reactants at the beginning. So you're going to have a big number minus a small number, which is going to give you a positive number. And in the same way, delta X is smaller than 0 for an exothermic reaction in which energy is released. At this stage, all of this sounds very, very abstract, but bear with me. I'm going to get to some graphs, and I think then it's going to make more sense to you. We're also going to look at the definition of an activation energy. That is the minimum energy needed for a reaction to take place. A good example of activation energy is the reaction that we saw in the beginning with the fire that's burning. In order for that carbon or coal to start reacting with oxygen, you first need to heat it, or you first need to light it. Okay, so you're adding energy. But then the amount of energy that's released, if you think of the big fire, is much more than the energy that you actually put in that little bit of heat that you had in the match. Okay, so that initial bit of energy that you need, that is called the activation energy. And during a chemical reaction, you have your reactants and your products, but in the middle you have something called an activated complex. That is, and we're going to discuss this also a bit later. We're also going to look at the influence of a catalyst in a certain reaction. Okay, so let's start from one point and just look at a few chemical reactions. What are we going to study? Now, these are just this is just a representation of a chemical reaction, which you also did in grade 9 already, where you had calcium carbonate and hydrochloric acid, and this gave you some products. Okay, we're not going to discuss this specific reaction. We're actually not going to discuss any specific reaction, but just a lot of theory that is associated with a lot of reactions. So in this reactions, the products or the chemicals that we have at the beginning is called our reactants. And then the chemicals that we have at the end is called our products. Oh, I see I made a slight translation error. Sorry, that N should have been and in English. So calcium carbonate and hydrochloric acid is going to be our reactants, whereas calcium chloride, these on this side, and carbon dioxide and water is going to be our products. The change or the arrangement of atoms changes as they go from reactants to products, and this steps in which they change is called the mechanism of a reaction. On a microscopic level, this reaction occurs over a few steps. Let me show you one quick example. If we have carbon dioxide that react with nitrogen monoxide, those two is finally going to give me carbon monoxide and nitrogen dioxide. But this reaction does not go immediately from the reactants to the products. In between, a huge molecule forms temporarily for a short while, and this molecule is called the activated complex. So this whole process, moving from reactants through the activated complex through to the products, is called the mechanism of the reaction. That's how the particles are moving. And in our observations on what's happening, a lot of that we're going to explain by looking at the movement of particles. And what happens if you have these different chemicals in a single container, then they are going to collide with each other. And we are going to look at these collision and form a collision theory, which we're going to discuss in a later video as well. The collision theory is used to explain the reaction mechanism, which is all about exactly how do particles collide with each other and ensure that a chemical reaction takes place. Okay, so let's have a look at the collision theory. For a reaction to recur, two things are needed. There must be effective collisions between reactants. Now, all the time these little molecules are bouncing, but let's just quickly look at this previous one over here. All the time molecules are bouncing or colliding with each other, but it doesn't always happen that bonds break and other bonds form. For new bonds to break and other bonds to form, these collisions must be effective. So in the exam, it is very important if they ask you when does a reaction occur, it doesn't only help to say you need a lot of collisions between particles. You need effective collisions, because some of these collisions result in nothing. It does not result in the breaking of bonds and forming of new bonds. So you need effective collisions, and then these particles must have enough kinetic energy to participate in reaction. How do we increase kinetic energy? Increase in kinetic energy is, remember, temperature is a measure of your average kinetic energy. So increase in temperature will increase your kinetic energy. The greater the amount of effective collisions, the faster the reaction will happen. What do I mean by a fast reaction or a slow reaction? Well, right in the beginning we saw the reaction of potassium with water. Do you remember that tremendous nice explosion in the bowl? That was a fast reaction. What is an example of a slow reaction? Well, if you put milk outside of the fridge for a day, it takes an entire day and sometimes more for that milk to become sour. That is a chemical reaction, but with a slow reaction rate. Even slower than that, if you take an iron rod and put it outside over a past few weeks, you will see that brown rust form on the top of that iron rod. That is an indication of a slow reaction. Okay, we discussed the forming of a activated complex. Here is just another example showing you the same type of thing. I have two molecules. I used the example of carbon monoxide and carbon dioxide that reacted. But here is just a general mechanism where we have bonds that was broken. The bond between C and B was broken, and a new bond between A and B had to form. But before that happened, all of these together form an activated complex, and this can only happen when we have effective collisions, and we will have more collisions if the particles are moving faster, if the kinetic energy of the particles is faster, so this will happen at a higher reaction rate. Now let's look at delta H. We discussed this a little bit when we looked at the exam guideline document. What exactly does delta H mean? It's also referred to as the heat of the reaction. The reaction heat delta H is the amount of energy that is absorbed or released during a reaction, and this is the important definition that you have to remember and have to apply. In order to calculate delta H, you need your energy of your products minus your energy of your reactants. In the beginning I spoke a little bit about this and told you there's different why delta H needs to be positive for an endothermic reaction and negative for an exothermic reaction, but we'll get to that. Reaction heat or enthalpy change, which is delta H, the other word for delta H, is measured in kilojoules per mole, or as the abbreviation goes, kg dot mole to the power of -1. Now let's get to the endothermic in exothermic reactions. If delta A is bigger than 0, if it's a positive number, if it's 300 kilojoules, it shows you that the action that they're talking about at that stage is endothermic. And if delta H is smaller than 0, then the reaction is exothermic. Let's explain that. An exothermic reaction is a reaction that releases energy, and an endothermic reaction is a reaction that takes up energy. So why is delta H positive for an endothermic reaction? Well, if the reaction took up energy, it means that the products must have more energy than the reactants. So if the products have more energy than the reactants, then the difference between these two must give me a positive number, and that is an endothermic reaction. If an energy of a reaction gave away a lot of heat, that means that my reactants or my products that form must have less energy than my reactants because a lot of heat was given off. So therefore, this will give me a negative number. Okay, let's continue. If we look in a practical side at exothermic and endothermic reaction, usually in an exothermic reaction, heat is transferred to the environment, heat is given off, so this reaction will heat the environment or heat your hand when you touch it. And in an endothermic reaction, it takes energy from the environment. So typically, if you touch this, it will take the energy from your hand and your hand will feel cooler. So typically, this reaction will be a cold one, or the temperature of the environment will decrease, or your hand if it's near it. And in this case, the temperature of your hand will increase. Okay, the difference between an exothermic and an endothermic reaction. Often in question papers, you will see that chemical reactions are represented in different ways. They can either give it to you like this, and then tell you what delta H is right next to it. Now this tells us, because delta H is a positive number, this immediately tells us that this first reaction is an example of an exothermic reaction. If we look at the second reaction, you can see that over here they are stating that delta H is smaller than 0. It's a negative number, so we know this is a representation of an endothermic reaction. Again, here we've got an exothermic reaction, and here they told us that the products are taking up energy to form the reactant, so this is an example of an endothermic reaction. If energy is released, then you won't have energy on this side. You will have your products plus energy, and that will be an exothermic reaction. Okay, so this one over here is an endothermic reaction, and if energy was on the other side, it would have been an exothermic reaction. You need to be able to draw potential energy diagrams, and if you understand them, these are quite easy marks in the exam. Okay, initially when we start with reaction, I'm going to look at two different types of reactions, endothermic and exothermic, but let's start. Initially I'm going to have my energy of my products. And then what is going to happen, this energy is going to, or I'll need to increase the energy, and this increase in energy is called my activation energy to form my activated complex. There we go. Okay, so this is my energy started and then the amount of energy increased. Just check my labels for my axis. This is potential energy, and this is as the reaction is proceeding, or the course of the reaction. So during the reaction somewhere I will have my activated complex forming. And then after new bonds are being formed, this is going to be release some energy, so that finally my energy of my products is over here. Now you can see my energy of my reactants was much less than my energy of my products. So this is an example of an endothermic reaction. And delta H, which is energy of products minus energy of reactants, is going to be a positive number. So for my forward reaction, this is going to be my reactants, and this is going to be my products. Reaction going to this side, I'm going to have the following values. If I need to read the energy of the reactants, that's going to be the value of X on my graph. The energy of the products over here, that's going to be the value of Y. The activation energy is this energy needed here. That's going to be the difference between Z and X. So it's going to be Z minus X. And my reaction heat, this number over here, that's my final energy, which is Y, minus my initial energy, which is X. That is the values for my forward reaction. But sometimes what happens, they will give you this graph and state and ask you some information on the reverse reaction. Now for the reverse reaction, it means that what used to be products in the final reaction is now going to be reactants. So in the reverse reaction, this is going to be the energy for my reactants, and which is going to be Y. My energy for my products will be X, because this is now the reaction happening in reverse for this component. And I will have my activation energy. That will be the amount of energy needed for this reaction to start. That will be Z minus Y, this value over here. And I will have my heat of reactions will be energy of my products, of my reagent, no, energy of my products there minus energy of my reagent. So that will be X minus Y, which will give me a negative number. Okay, so in this case, if I look at this reaction, the forward reaction, if I had a reaction A plus B equals C plus D, the forward reaction would be A plus B equals C plus D, and that will be an endothermic reaction. The reverse reaction, which will be C plus D equals A plus B, that will be an exothermic reaction that I read from this side. Okay, if they initially gave me the graph like this for my forward reaction, this will tell me that my forward reaction is now an exothermic reaction. Okay, let's look at the same values over here. Initially, I have my energy for my reactants, which is going to be this value Y. I see I have my label slightly down there. It's probably from my other graph. It should have been up here. That is the energy of the reactants. The energy of the products is down here. It's the value of Z. X, I mean, this value here, X. The activation energy for my forward reaction is the minimum energy required for this reaction to take place. It will be this amount, which is Z minus Y. and my reaction heat for my forward reaction is going to be my products minus my reactants, so that's going to be X minus Y, and that is going to give me a negative number. For the reverse reaction, the one that I read from this side, so if I have my forward reaction A plus B gives me C plus D, then my reverse reaction would be C plus D gives me A plus B. This is appropriate for a reversible reaction, and we're going to talk in the next couple of chapters about the difference between reversible reactions and reactions that occur in one side as well. If I have a reversible reaction, and I read my reverse reaction from this side, then this would be my energy for my reactants, and this one will be my energy for my products, which is why my activation energy will be the minimum energy needed to form the activated complex, which is then the difference between Z and X. And my reaction heat, which is always my products minus my reactants, will be Y minus X. And for my reverse reaction, this will be a positive number, and my reverse reaction is an endothermic reaction. Okay, we've discussed activation energy. I've shown you in the previous graph what this is about. You need to know the definition. It's the minimum energy needed to start a chemical reaction. And here I've shown you this is the activation energy for an endothermic reaction. Endothermic because my initial energy is less than my final energy, so energy is taken up. And this is my activation energy for my endothermic reaction. Let's look at the influence of a catalyst. Now, what a catalyst does, it increases the rate of the reaction by creating an alternative route for the reaction with a lower activation energy. And often they will show you, please indicate on this graph, how the catalyst will have an influence. And it will just lower the activation energy, so this bend will be slightly lower. Okay, there I indicated it on both graphs. Our activation complex or activated complex, we spoke about that as well. This is where I indicate on my graph where my activated complex forms. Okay, and that sums up a lot of theory. You'll probably have to go through this video once or twice more. It's not so much work to understand, but it's a lot to study. And after you are sure that you understand the theory, why don't you go through this sum to make sure and see that you can do all of this. I will give, as always, the solutions in our next video. Have fun.